Okay, in the last recording, I ended up talking about how, electrons eventually reach the ground state. All right, and actually the opposite is what happens for the absorption spectrum. You have photons coming in. I think there's a graphic of this, very nice. They'll come in, and the electron will be in the lower state, and then it'll jump to a higher state. And so that energy difference between the lower state and the higher state is what gets absorbed. Okay, so I'm just kind of moving towards absorption. So emission, the energy drops from a higher state to a lower state. So there's the modern. That's nice. They're showing the modern explanation of electrons, that they exist in really clouds. And so there's the cloud in the ground state. It's not precisely, the way we used to think of it. It has to be at one specific location, but anyhow, it exists in a probability, and then, of course, in the excited state, it exists in a larger probability volume. This is actually a volume because these things are three-dimensional. All right, so this is actually showing you the equation. That we're not actually going to do any of these calculations, but this is the energy for a hydrogen atom. So, in fact, these are they're showing you when the electron jumps from from the n equals 2 to the ground state, or the n equals 3 to the ground state. It's showing you what these different emission spectra would be. It turns out that these the ones when they jump for hydrogen, when the electron jumps from a higher state down to the ground state, this was actually discovered long before quantum mechanics was able to explain these transitions, or these emission lines. And so this is an area called the Lyman series, as it says right here. These are all in the ultraviolet. And then the Balmer series is the most famous one. This is the electrons jumping down, right? So it's in an excited state, and then it goes to this intermediate state, the n equals 2 state. So it's not all the way to the ground state, but the nice thing about these and why it's so famous is these correspond to, and they're actually showing you the colors. When it drops, when the electron's in the n equals 3, the end state, the n's just mean the different. They just range from 1 to infinity, basically. They correspond to different energy levels. The higher the number, the higher the energy level. So when the electron's in the n equals 3 and it drops to the n equals 2, as all of them do with the Balmer series, they always drop to the n equals 2. You get a visible wavelength, so that which corresponds to red light. And if it's dropping from the n equals 4 to the n equals 2, you get kind of an aqua. They're showing it more green here, and then you get a blue line if it drops from the the next highest one, n equals 5. Anyhow, that's the idea of where these things. We actually understand this quite well since the discovery of quantum mechanics. All right, we'll talk a little bit about what's called the photoelectric effect. This is actually what Einstein won his Nobel Prize in Physics for. Was explaining the photoelectric effect. A lot of people think he won the Nobel Prize for the theory of relativity, but that is not the case. So this is what some people discovered, and Einstein correctly described using quantum mechanics, which this was the very beginnings of quantum mechanics in the early 1900s. Anyhow, you shine light onto a metal, and sometimes the metal would start to conduct, and which basically means electrons get emitted by the metal. And then people noticed that it had more to do with the frequency. Remember, higher frequency would be, for example, purple light, right, would have a much higher frequency than red light, right? Red light, as far as the visible spectrum is concerned, red light would have the lowest frequency. Purple light, the deepest blue that the human eye can see, would be the higher frequency. And then, of course, you go a little above that, you get ultraviolet frequencies. And actually, a lot of this experiment dealing with the photoelectric effect dealt with ultraviolet frequencies. Anyhow, when you increase the frequency, you got more electrons. That, of course, the reason that these were measured is because moving electrons. That is really what current is, right? And so that could actually be measured. So we could measure the increase in frequency of the light, and we got a corresponding increase in the energies of the photons. But if let's say we just took a light, a red light, let's say, and we aimed the light at up that same piece of metal. And no matter what the intensity was, you didn't get any more electrons. And any electrons that came out all had the same energy. So it really didn't have to do with the brightness of the light or the intensity of the light. It really had to do with the frequency of the light. So there must be some relationship between energy and frequency. Of course, that's actually showing what's going on right here. So a particular piece of metal is you have infrared light, which of course is less energetic light than any part of the visible spectrum, and you don't get any electrons, right? You don't get any current. This is for a particular piece of metal. Different metals correspond to different wavelengths, of course, or, get the electrons excited with different wavelengths. So there are metals where infrared light would, but let's say this particular metal, no electrons, no current. Red light, no current. Blue light, you start to see some current, right? And then when you get to ultraviolet light, you get even more current, right? So it has to do with the frequency. Higher frequency, you get higher energy, more electrons, higher energy electrons. And then, as you go down, and so like with red light, let's say, you get to right at the cutoff, then what happens is right at the cutoff, no matter what the intensity of that particular light is, no electrons will flow. You don't get any electrons emitted from the metal, and so you don't get any current. So even making this super, super bright, you still don't get anything. All right. So this is the equation that actually there was a guy named Planck that discovered this equation, and then Einstein used this and some other ideas, basically the conservation of energy. To explain this photoelectric effect. But this is really important to us in physics and astronomy and chemistry as well. So the higher the energy, the higher the frequency. The energy and the frequency are related through what's called a constant. There was a guy named Planck who discovered that constant. There's the numerical value for it, 6.63 times 10 to the minus 34th, and the units are joule seconds. Just to make that complete. All right. So what about absorption lines? Basically, with that, you have let's see. Is there a nice pictures of that? You have the light. The light comes along, and what's going to happen is the light gets absorbed. So it'll cause the electron these photons will come along and cause the electron to jump into a higher state. But not just any photon will do. It has to be a photon that is exactly the amount of energy between one state and the other. It can be any higher state, it doesn't matter, but it has to be exactly equal. In fact, the difference between these energy states is what we call a quantum. That's where the idea comes from. All right, so anyhow, that's the idea of absorption spectrum. All right, so they're just showing you, with just regular old atoms, individual atoms. The absorption spectrum, has been observed over a long. The absorption and the emission spectrum has been observed. When you have multi-electron atoms, you get a more complicated spectrum. We were looking at that, like for example, mercury or iron or something like that. It also makes a difference if you have ionization. That is, if the atom has unequal numbers of electrons and protons. If they're equal numbers, you get this stuff up here. When it's ionized, you get a different spectrum. And so we can tell. We can actually tell whether the gases that we're looking at in space are ionized, and what they're made of. And the other thing that you can tell is not just can you identify the atoms, you can identify the molecules to some extent if they're not complicated molecules. That's actually showing you here. Carbon monoxide or something like that. You get very specific spectral lines. I guess they're showing it down here. You'll get very specific spectral lines for different molecules. Usually simple molecules, nothing complicated. You don't get large organic molecules that you observe in space. We just we don't have the technology as of yet. I don't know that'll ever happen in our lifetimes to observe really complicated molecules. Hopefully we will. All right, so just to keep in mind, molecular spectrum are much more complicated, but we can match. If we get a molecular spectrum, we try to match what's observed with what we know about, and let's see. So you can tell what the chemical composition is. Remember, with that thing called Wien's law, you can tell what the temperature is, and you can also use the overall movement of the spectral lines. So the spectral lines move as one. So let's say it's hydrogen, because that's the most common thing that we find in the universe. Those spectral lines, if they've moved either to the red end of the spectrum or to the blue, but they move as a pattern. So the same pattern, but they've moved either in the red direction, and so that means if something's moved in the red, and so all these lines would move correspondingly to the red, and the amount that it moves to the red corresponds to how fast it's moving. Either moving away from us, that's what recession means, or moving towards us. That's what approach means. And in fact, that's one way in which we can look at planets going around other stars. We'll talk about that later. So this is another thing to also consider when you're looking at spectral analysis. Is there's different things that can cause the spectral lines to widen. So let's look at some. So you can just read this list here. Let's see. So temperature, turbulence, rotational speed, density, magnetic field can all cause the lines to widen. All right. So let's see. I'm almost done here. Let's. How many more slides do I have? All right. So I might have to finish on the next slide. I'm really close to being done, so I'll make one short video and complete this chapter. All right, I'll talk to you guys in the